right, guys, so one of the interesting things about this car is it does have a stepper idle valve conversion done to this Foxbody. Now, I'm letting the car cool off right now because I just got done with most of the steady state tuning before we get into ramps. So let's take a quick look at the conversion that was done on it, and then I'm going to show you what some of that looks like in the software and how I arrived at the settings that I'm using to get a nice clean drop back into idle. Let's take a look. All right, don't mind the bit of wiring mess going on. Obviously, they just did some of the conversion, and most of this is just kind of laying out of the way instead of being tucked, just in case we need to get to it to make any changes during this installation process. Once everything is working, it'll all get tucked away nice and clean, as you would expect any build. Now, one of the couple things that I asked them to do was to put an air intake sensor right here in the intake tube. Why? These Foxbodies are notorious for intake air temperature heat soak. And that's a phenomenon where the metal surrounding the sensor causes a very high temperature reading. Normally, it is right here in runner number 5 on the small block Ford, and that sensor is very hot to the touch currently. Now, Ford had a great reason for doing this. Ideally, you want to get the temperature reading right where it goes into the valve. And while in theory that works out great, with these large cast aluminum manifolds and the relatively slow change in temperature reading on a thermistor, we get this heat soak effect. And you can see that where in a typical Foxbody, your intake air temperature sensor is going to start matching the coolant temperature. At any extended idle or after a run, the temperature will come back up. It's pretty obvious when you start a pull on the dyno or you start a run at the track, you can actually see the intake air temperature go from about coolant temperature, and it will begin to drop rather drastically as the vehicle picks up speed. But it will never make it down to ambient temp. Now, they've got a nice hot air intake on this car currently, but with the intake air temp sensor, or the matte air temp sensor, or IAT, installed in the intake tube here, once they get this filter out of the engine compartment, what we should see is about a 30 to 40 degree Fahrenheit over ambient temperature reading that will quickly drop to ambient temp, or right around ambient temperature, once they're actually under speed on track. And that's going to get us much better manifold air temperature fuel trims in the long term. Now, stepper valve. The stepper, this Foxbody has been converted from a PWM valve to a stepper valve. And while they tune very much the same, some people seem to believe that a stepper valve is a little bit more accurate than a PWM valve. I don't really see much of a difference tuning-wise between the two. This stepper valve, really it needs a little bit more of a gasket around the pintle. What's happening is there's a very narrow range that this stepper valve actually works in for controllable idle speed, even though I've reduced the angle of the throttle quite a bit from when it came in. The lowest idle speed I could achieve with the idle valve fully closed and only about 5 degrees of ignition timing in this motor was around 850 RPM. I reduced the throttle by about 10% opening, and now I can easily achieve a 750 RPM idle speed. However, the engine's not really happy around there, so I target to maintain about an 850 RPM idle speed. Now let me show you in the software what I did to get the values that we're using to get this not only idle speed and control, but to make sure that it drops back into idle appropriately. All right, guys, so let's take a look at the settings I used for idle here. So, like usual, I kind of set everything up in closed loop idle. So our idle control is set to closed loop. I'm using some rather small time step sizes and whatnot. I really prefer to home a stepper valve open rather than closed. The reason why I like to do that is if you just jump in and turn everything on and hit the start button, what you may run into is if you're homing closed rather than open, you may catch the valve in the full closed position during a crank. If that happens, then the valve's going to be closed and you're going to get a really low or slow idle speed, or maybe a start and stall condition. And to stop that, I home in the open direction. Now, on all of our new ECUs that will be coming out, especially this prototype competition series ECU, we have gone to much better stepper chip, and I can just leave power on for always on for power between steps. Okay, closed loop idle here. Now, what I found after I lowered the amount of throttle angle by backing out that idle screw is that we get our lowest idle position at around 60 steps. Now, above 140 steps, we have a very, very high idle. Although I don't really set a maximum, I just left the idle valve maximum steps at 250. I'm adding 5 steps for a dash pot adder. When we're dealing with our closed loop tuning, something to remember about closed loop PIDs is that this is a C-type loop. The C-type loop means you're going to tune your I first, then your P term, and then finally, if necessary, add a small D term. So I is basically what you're going to focus on for idle loop tuning 100% of the time. Then you add P term in small amounts until you get an appropriate response to an immediate idle change. And then you only add derivative term if you absolutely have to. I use a value of 1 out of habit. Anything above, say, 5 to 10 on your derivative gain is going to slow the loop down substantially. So this is the reason why I'm using 75P, 165I, and a derivative of 1. Here's my initial values, and here's my closed loop target idle curve. So you can see I'm targeting an 800 RPM idle speed once the engine is fully warm, and I've got 111 steps set for that idle speed. Now, that does not mean that when we're at idle, we're going to be sitting at 111 steps. That means that when I blip the throttle, or I clutch in, or I come off, as the idle drops back down, I want to start at 111 steps. And then closed loop is going to lower that value to get me down to my stable idle speed. So when we start the car and we let it idle down and I blip the throttle, you're going to see the idle stepper go between 111 and 116 because we are adding 5 and the dash pot adder. And then you'll see closed loop idle kick on, and then the stepper valve will close to drop the idle the rest of the way. And how I set this is when the engine is hot, I sit here and I change this to different values, 800, 900, 1000, and then I figure out what initial value do I need to get a nice clean drop into idle. I always want to come in slightly above the idle speed I want and then drop in cleanly. Now, An engine like this that's got a very choppy cam, we cannot just look at the idle valve. My idle advance settings here, that's this timing correction curve and my idle advance timing. What this means is that as soon as we go into an idle state, instead of using the ignition table, I am going to use this idle advance timing curve right here. So when my fuel load is low, when I'm under heavy vacuum, I'm going to use this advance value, and then this advance curve is going to be modified by this timing advance curve. And these two work together to maintain a strong, solid idle speed. So you're not going to be able to hear me talking while this is running because the engine is so loud. We're going to try and see what we can get out of the audio. But what I'm going to do now is I'm going to start the engine, and I'm going to show you how this drops back into idle, so you can see how I go through the process and what we get out of it. What we're going to focus on is I'd like you to focus on the RPM, the stepper position, our target, ignition timing right here, and our air-fuel ratio. Those are the most important things to focus on when you're tuning idle, okay? Your ignition timing is very important for how the engine's going to idle. Your air-fuel ratio needs to be stable. And if you're excessively rich or excessively lean, that's definitely going to affect the quality of the idle that you get out of the vehicle. So on that restart, it was pretty lean. Now, I wasn't recording the screen, so you don't know how lean, but I'll tell you, it was lean. I had about an 18 air-fuel ratio that was displaying. So what I'm going to do is extend my ASE taper, because the car has been sitting for about 20 minutes since it was last started. And now that I've extended that ASE taper, I'll show you how much I added to it, and then I'll show you the difference. Okay, so we had that really lean restart. So after start enrichment is one of those things that's very important when you're dealing with a hot engine. And I had a scenario here where on a restart, I had a very lean air-fuel ratio. So looking at our taper value here, and I had this taper at 1250, and that wasn't keeping the fuel in long enough to rebuild the fuel in the intake manifold to get us back down to our normal stable air-fuel ratio. So what I'm going to do is I multiplied by 1.8 when it's super hot here and really extended that taper out quite a bit. And what we're going to do is restart and see how lean are we this time. Now this is our competition ECU has a built-in wideband, so we're just going to let it go through its warm-up process. And you can see the ASE taper is sticking around for a much longer period of time. We're adding quite a bit. We're adding fuel for much longer than we were previously. And the idea is we need to keep that fuel around to rebuild that layer. And as that fuel finally disappears, we can see that we are back to our normal stable air-fuel ratio there at idle. All right, now that that's complete, let's go back to talking about closed loop. Now, we can see that I'm sitting right around 70 idle steps currently. Now, what I want you to do is when I flip the throttle, watch how many steps that goes to. Right here, you can see our dots pointing right at this column. We're going to pull 111 steps plus the 5 steps from right here for our dashpot adder for 116 total. The idle should come in a little high, right around 1,000 RPM, and then settle in to 800 in a reasonable amount of time. Okay, nice response. So the idea here is we want the idle to come in above our target and then settle in nicely so we don't end up with a stall condition. I'm pretty happy with that. Now, what I did to derive these values is I set my target in closed loop, and then I simply went through and figured out what value do I need. So let's set a value of 900. Now notice we went to a higher number of steps because we're now pulling from the 900 column. So 115 plus the 5 should give us 120. You can see we come in above our 900 target and then settle in nicely. This is just a bit of trial and error on my part. What I did is I set my value and then I adjusted my initial value column until I got the idle to drop in how I expected. You can see it drops in nicely. Exactly what I was hoping for. Now, for that really low idle, because this has got a super chop cam in it, sounds really good. I do not like to drop directly into idle at this low idle speed with a choppy cam like this. That's just asking for stall condition issues. That's why I add more steps or PWM percentage than necessary to get the idle to drop in as expected when I need it to. I'd rather have a slightly high idle when it drops in and then let it come down over time than have a stall condition. Now, These initial values are only half of the equation. Ignition timing plays a crucial role in how well the vehicle is going to drop into idle. We can see that right now, we're pulling about 15 degrees of ignition timing from our curve because we're in the idle state. And we can see our ignition timing in real time is moving around. Why? Well, it's being adjusted by our timing correction curve. And the timing correction curve is using ignition timing to control our idle speed, or help control our idle speed. Ignition timing is much better at controlling idle speed right now. I like to think of ignition timing as instant changes to idle speed, and the idle valve is a slower change for idle speed. Now, this works very well with choppy cams or large cams. A lot of your N-line or smaller displacement motors may actually become upset with this amount of timing correction. Let me show you what happens to the idle if I remove this timing correction. I'm just going to take these and set them to 0. See, it takes a minute, but the idle speed is not quite as clean as we'd like it to be. It doesn't stay as close to target. See how it's dropping down into the 600s before climbing back up? Now I'm going to put that back. We can see that we're maintaining our idle target much tighter. As a matter of fact, these are actually rather easy values. I can tighten up right here, right around my 0 point. And what this means is that when we get negative 25 below target, we're going to add 2. When we get 25 above, we're going to subtract 2 degrees of timing. And now we can see that we're maintaining our idle target much, much tighter. You can get even more aggressive than this if necessary. It really depends on the application. But I don't like to get too aggressive because it does take away the chop of the cam. Okay. Now, let's watch what happens when I change things a few times. I am going to make all of this 15, and we're going to see if the vehicle stalls. See how much slower the idle dropped, and you hear the backfires? That's because ignition timing was much lower as we came through that decel region. We do drop back into target much faster, but the concern here is on track or under normal conditions, we may have a stall. Watch what happens when we add a little bit of timing in that decel region. See how the idle slows down a little bit in its descent? So it slows the idle drop, and it makes it a bit cleaner as it drops in. You can get too aggressive though. See how slow that was? We don't want to get too aggressive with that. That's a nice drop in the idle.